A frustrum of a cone. A frustrum of a cone has smaller radius capital R1, larger radius capital R2, and length L, and is made from a material with thermal conductivity K. Derive an expression for the conductive heat current through the frustrum when the side with radius R1 is kept at temperature TH and the side with radius R2 is kept at temperature Tc. So I'm assuming that this is the hot side and this is the cold side. So if you look at your frustrum of a cone, so the side with radius R1 is cold, the side with radius R2 is hot, so heat will flow from hot side to the cold side, and if this is our x-axis, let's put the smaller radius side at x equals 0 and larger radius side at x equals L. Okay, so let's write the law of thermal conduction. Law of thermal conduction says the heat flow per unit time, the heat current, dq divided by dt, which is power, is the thermal conductivity K area multiplied by dt dx. And when we write this law, we have to be careful about the sign of K. So the sign of K has to be positive. So if you look at my schematic drawing here, so from x equals 0 to x equals L, the temperature is increasing and x is increasing. So dt dx is positive in this direction, and dq dt normally will come out to be in the negative direction. So therefore I should mention here that this is actually absolute value that I'm talking about. So absolute value of dq dt is ka dt dx. Okay, so k is positive. The area, the surface area is positive, dt dx. Obviously, the surface area is changing as I go from x equals L to x equals 0, so I have to take that into account. So if I consider a slab with thickness dx, so let's do that. For a slab with thickness dx, so that's on the path of the current flow. This law is going to tell me, because this has radius r here, which depends on x, it's the area pi r square k times pi r square dt dx evaluated at position x. So because I put this at position x, this is evaluated at position x. All right. And what do I know about steady state heat flow? At steady state, the rate of heat flow from right to left will be the same in each such slab. So if I look at another slab here, this slab or this slab, what I will see is that the rate of heat flow will be the same, because that's the steady state condition. So that's right here. At steady state, for each such slab, I must have P, the rate of heat flow, a constant. So that's the conductive heat current that it is talking about. And this is true for all such slabs that I can consider on the path of the heat flow. Now, as I said, because this radius is changing as I go from x equals L to x equals 0, I have to take into account the radius as a function of x here. So that's my first task. So I notice that the radius is changing linearly with x let's write this as ax plus b. A and b are coefficients. And put the boundary condition when x is equal to 0. When x is equal to 0, the radius is r1, capital R1. So that is b, and b must be equal to r1. When x is equal to L, here, I can see that the radius should be r2. So when I substitute x equals L here, I will get AL plus B. So AL plus R1 must be equal to R2, which tells me A is R2 minus R1 divided by L. Okay, so that I can write the radius as a function of a distance from x equals 0, R2 minus R1 over Lx plus R1. If you wish, you can check again. If x is equal to 0, this would give me R1. If x is equal to L, L's would cancel. R2 minus R1 plus R1 would cancel. I would get R2. Okay? Then I can write the rate of heat flow as P is equal to K pi R squared, where R is now given as a function of x, R2 minus R1 over Lx plus R1. This is my radius squared, pi R squared, dt dx, where this is evaluated at position x, right? So that is where this lab is. Now, if I look at the variables in this equation, if I try to separate the variables, temperature and x. So let's collect x's on one side and temperature on the other side. So I can see that P dx divided by this radius squared, which is ax plus b squared, let's keep it in this form for the moment, must be equal to k pi dt. So if I integrate both sides, so if I integrate this from 0 to L, this is going to be from the cold side, T cold, to the hot side, T hot. That's where the temperature is TH. And in order to perform this integral, I also note that the power in all such slabs is a constant, so it's going to come out of this integral. I let, in order to perform the integration, ax plus b equals y. And this tells me that dy is a dx. So this integral turns into y at x equals 0, y at x equals L. Then I have P, for dx I substitute dy over a, and for ax plus b squared I have y squared. So this integration is minus P divided by a, 1 over y, evaluated between y at x equals 0, y at x equals L. So the derivative of y to minus 1 is minus 1 over y squared. So that's basically the integral I obtain. So if I substitute for y ax plus b, this becomes minus p divided by a, 1 over ax plus b, which will be evaluated between x equals 0 and x equals L. So that will give me minus p over a. At x equals L, I obtain R2, 1 over R2. and then plus P over A. At x equals 0, I obtain 1 over R1. Okay? So this is now equal to P over A parentheses. I have R2 minus R1. So this will be R2 minus R1 divided by R1, R2. So let's make the common denominator here. And since A is equal to R2 minus R1 over L, so this will be P divided by R2 minus R1 over L, which is my A, multiplied with R2 minus R1 over R1, R2. So R2 minus R1s will cancel. So this will get rid of this R2 minus R1. And I will be left with PL divided by R1, R2. So that is the left-hand side of this integral. The right-hand side is simple. It is equal to K pi delta t, t hot minus t cold. Integral of dt is delta t. And this must be equal to PL over R1, R2. That is the left-hand side of the equation. And here I can see that P must be equal to, if I collect all the terms except P here, this will be K pi thermal conductivity times pi T hot minus T cold divided by L multiplied with R1, R2. So that will be the rate of heat flow through the frustrum of the cone. Now you can see here if R1 is equal to R2, this would be K pi R squared TH minus TC over L. So that would be a simple cylindrical system. So this is basically one limit we can check for this result. All right, so we're talking about a frustrum of a cone. So that's a cone that is cut at one end here. So the bottom has radius R2, the top has radius R1. It has thermal conductivity K and length L. So if I look at the heat flow, it has to be from the hot to cold side. I want to know at steady state what is the conductive heat current through the frustrum of the cone. I write the law of thermal conduction Ka dt dx. So the dt dx is positive because temperature is increasing as x is increasing in the setup that I have shown here. So that's equal to the absolute value dq dt. All right, so for a slab with thickness dx here that I choose at point x, this will be k times pi r squared, the surface area through which the heat is flowing, and dt dx evaluated at position x. For all such slabs at steady state, the rate of heat flow will be the same. So this P should be a constant for all the slabs. All right. So one thing I notice is that this radius is changing as a function of x. For example, x equals 0, it's R1, x equals L, it's R2. And I write this as a linear function of x, and by putting the boundary conditions, I find that r as a function of x is R2 minus R1 over Lx plus R1. So I can substitute that for r so that the power will be, or the rate of heat flow or the conductive heat current is K pi R2 minus R1 Lx plus R1 squared dt dx evaluated at x. So if I collect the temperature on one side and the x terms on the left side, since P has to be constant through all such slabs, if I integrate from 0 to L, P dx over ax plus b squared, that must be equal to the integral Tc to Th K pi dt, where P is a constant coming out of the integral. This integration is performed by substituting y for ax plus b, so transforming from x to y. We notice that the integral gives us minus 1 over y, and evaluating between 0 and L, we obtain PL over R1, R2. If we substitute for A, R2 minus R1 over L. And the right-hand side is K pi delta T, Th minus Tc. So we can solve for P from this equation, and the answer is K pi delta T over L, R1, R2. And as I said, if R2 was equal to R1, this would become R1 squared, K pi R1 squared, Th minus Tc over L. Then this would turn into a cylinder, and that would be exactly the answer that you would have, because R would not be changing as a function of x, so that checks our result in one limit.